There is an equation, written in 1961 by an astronomer named Frank Drake, that tries to estimate how many civilizations we could hear in our galaxy right now. It is a string of factors multiplied together. The rate stars are born, the fraction with planets, the chance life begins, the chance it gets smart, the chance it builds radios, and then, at the very end, one last term, the letter L, how long a civilization lasts once it can be heard. Drake and the people who worked on it noticed something uncomfortable almost at once. Every other term in the equation you can argue about, but L swamps them all. Make life common, make intelligence likely, and it does not matter, because if civilizations die young, the galaxy is empty of voices anyway. The whole question of whether we are alone comes down, in the end, to a single number nobody can measure. How long do they last? And we have exactly one civilization to study, ourselves, about 100 years into being able to be heard. So here is the question that should keep you up. What if the answer is not long? Tonight, we are going to take the last term in the Drake equation seriously and ask whether the thing that ends civilizations is not bad luck, but something built into what it means to become powerful. By the end of this, you will understand why the lifetime of a civilization may be the only number that matters, why the same window that makes a civilization loud may be the window that ends it, and why the silence we hear is exactly what a universe full of short-lived civilizations would sound like. I am not going to tell you we are doomed, but I am going to tell you that lasting may be much harder than arising, and that nobody yet knows if anything has ever managed it. If you like the kind of question that sits with you after the video ends, a subscribe is how you tell me to keep making them. Now, let us begin. Let me put the whole equation in front of you, because the argument tonight lives inside one piece of it, and you cannot feel the weight of that piece until you see the rest. In 1961, Frank Drake was organizing the first real scientific meeting about searching for alien civilizations, and he needed a way to structure the conversation, a way to break the impossible question, are we alone, into pieces you could actually talk about one at a time. So he wrote down a chain of factors that, multiplied together, would give you a number. Call the number n, the count of civilizations in our galaxy right now that we could potentially hear. And to get n, you multiply 7 things in a row. You start with how fast stars are born in the galaxy. You multiply by the fraction of those stars that have planets, then the number of planets per star that could support life, then the fraction of those that actually develop life, then the fraction of living worlds that develop intelligence, then the fraction of intelligent species that build a technology capable of sending signals into space. And then, at the very end of the chain, after all of that, one final number, the average length of time such a civilization stays detectable, how long it lasts, the letter L. The equation was never meant to be a theory of alien life. It was meant to be honest about ignorance, a way of laying out exactly which questions stand between us and an answer, each unknown set down in its place, so you could see the whole shape of what we do not know. And that is why it has lasted. More than 60 years on, we are still using it, still arguing about its terms, still finding that this one short string of factors holds the entire problem inside it. Every term in it is really a question about the galaxy. How often does a star light up with planets around it? How often does one of those planets wake into life? How often does that life look up and start to wonder? And then at the end, the question that turns out to matter most, once a world has woken up and started sending its voice into the dark, how long does the voice last before it falls silent? Now here is the thing that hides inside that structure, and it is the hinge of this entire video, so I want to be careful with it. 6 of those 7 factors are about getting started. They are about how hard it is to go from a cloud of gas to a planet, from a planet to life, from life to a creature that can build a radio. Those are the factors everyone loves to argue about, because they feel like the deep questions. How rare is life? Is intelligence a fluke? And those arguments are real. But notice what the structure of the equation does. The first 6 factors tell you how often a new civilization switches on, how often a new voice could begin somewhere in the galaxy, and then you multiply that rate by L, by how long each voice lasts. And it is that final multiplication that actually decides how many voices are speaking at once, right now, for us to hear. The way I have come to think about why this one term dominates is to picture a long recipe. Imagine a recipe with 7 steps and you follow the first 6 perfectly. The finest ingredients, the precise measurements, the careful mixing, everything flawless. And then the last step says leave to set for the right amount of time, and you take it out after 4 seconds. It does not matter how perfect the first 6 steps were. You have a puddle, not a cake. The final step, the setting, has a kind of veto over everything that came before it, because it governs whether all that careful work ever becomes the thing it was meant to be. L is the setting step. You can have a galaxy that does the first 6 steps beautifully, makes stars and planets and life and minds and radios with great reliability. And if the last step is too short, if the civilizations do not hold together long enough to set, then all that flawless work collapses into silence anyway. The final term does not just contribute to the answer, it can quietly overrule everything else. Think about what that means with a simple version of the numbers. Suppose the galaxy switches on one new civilization every year, a new voice once a year, somewhere among the hundreds of billions of stars. If each of those civilizations stays detectable for say 1 million years, then at any given moment there are about 1 million of them out there talking, because each one is still going while 1 million more switch on behind it. The galaxy is full of overlapping voices, but now keep the birth rate exactly the same, one new civilization a year, and change only L. Say each one lasts not 1 million years but 100 years. Now at any given moment, there are only about 100 of them detectable in the entire galaxy, 100 faint voices scattered across an ocean of hundreds of billions of stars. Same number of civilizations being born, wildly different galaxy. One is crowded, one is all but silent, and the only thing that changed was L. That is why Carl Sagan, who worked on all of this in the years after, said something that has stuck with me. He said that all of our arguments about the other factors, all the fierce debate about how rare life is and how likely intelligence is, all of it pales before our uncertainty in L, because the others, at least in principle, we can get at. We have learnt since 1961 that planets are everywhere, that most stars have them. We are making progress on the chemistry of how life might begin. Those front-end numbers are slowly coming into focus. But L is different. L is not about beginnings, which we can study by looking at the universe making new things. L is about endings, about the fate of civilizations, and we have never once watched a civilization run its full course from beginning to end. We have no examples, none, except, possibly, the one we are sitting inside, and that one is not finished. It is worth appreciating just how much the front end of the equation has firmed up since 1961, because it sharpens the loneliness of the last term by contrast. When Drake wrote it, we did not know whether other stars even had planets. We had not found a single one. The fraction of stars with planets was a pure guess. Now, after decades of work and missions built to hunt for them, we know that planets are not rare at all, that most stars have them, that our galaxy holds billions of worlds, many of them roughly Earth-sized, many at the right distance from their stars for liquid water. One after another, the front-end terms have moved from total guesses toward real measurements, and almost all of them have moved in the generous direction, toward a galaxy rich in planets and possibilities. So the trend of the evidence has been to make the beginning steps look easier, more common, more favourable, which means that if the galaxy is nonetheless silent, the pressure of explaining that silence falls harder and harder on the one term that has not moved at all, the one we still cannot measure, the lifetime. The more ordinary the front of the equation looks, the more the silence points at the end of it. And there is a deeper trap in trying to measure L that I want to name now, because it shapes everything. With every other term, you can improve your estimate by gathering more examples. Want to know how many stars have planets? Look at more stars. Each one you examine sharpens the number. But L is the lifetime of a finished civilization. And to add an example to your data set, you would need to watch a civilization run all the way from its first broadcast to its last, beginning to end. We have never done that. We cannot do that for ourselves, because we are not finished. And we cannot do it for anyone else, because we have never found anyone else to watch. So L is not just uncertain in the ordinary way, where more data would help. It is uncertain in a deeper way, where the data is almost impossible to get, because the thing being measured is an ending, and endings are exactly what the silence hides from us. We are trying to estimate the average length of a story, having never once read one all the way through. And how long has that one been detectable? About 100 years. We started leaking radio into space in the early 20th century, and that is the entire span of our existence as a thing that could be heard across the dark. 100 years, against a galaxy that is more than 13 billion years old. So when we try to estimate L, the most important number in the whole question of whether we are alone, we are doing it from a single example that is 100 years into a story whose ending we cannot see. The data is one data point, and it is still being written. And there is a subtle trap in being that one data point, which is worth flagging now because it shadows everything that follows. We are tempted to reason, well, we have survived 100 years, so 100 years is clearly survivable, and probably more. But that reasoning is bent by the simple fact that we have to exist in order to ask the question at all. Only the civilizations that have so far survived are around to wonder about their own lifespan. The ones that ended at year 50 are not asking anything, so our own continued existence cannot tell us much about how dangerous our situation is, because we would find ourselves alive and wondering in exactly the same way whether long survival is common or astronomically rare. A creature that has only ever survived cannot conclude much from its survival, because survival is the precondition of its asking. We have to hold that humility the whole way through. Being here, having lasted a century, feels like evidence that lasting is possible, and it barely is, because we are the only ones who could ever have noticed. It would be like trying to estimate the average human lifespan, having only ever met one person, a 100-day-old infant, and being asked from that alone whether people tend to live for months or for decades. You simply cannot tell yet. The data is one data point, and it is still being written. I find it useful to picture the whole thing as a struck match, a civilization that becomes technological, that learns to send signals into the dark, is like a match flaring to life in a pitch-black room. For a moment it is bright, unmistakable, visible from across the room if anyone happens to be looking. That flare is the civilization becoming detectable, becoming loud, and the question the Drake equation forces on us, the question hiding in that final term, is not whether the match lights. Lots of matches light. The question is how long it burns before it goes out, and whether, in the brief time it is lit, anyone across that enormous dark room happens to be looking in exactly the right direction. So if L is the term that decides everything, we have to ask the obvious next question. Why might L be small? Why might the match burn fast? And the first answer, the one almost everyone reaches for, is the one Sagan reached for. Civilizations might destroy themselves. Carl Sagan set L at 100 years, and he had a specific reason, and the reason was that he had watched it happen. Not the ending, but the setup for one. He had lived through the moment when a civilization, ours, first gained the power to be heard across the stars, and the power to end itself, and he had noticed they arrived almost together. That is the self-destruction hypothesis, the oldest and most intuitive answer to why L might be small, and it is worth taking seriously before we go looking for anything deeper, because it might just be correct. Picture a single human life spanning it. A person born in the year 1900 would have grown up as radio was first filling the air with human voices. The first time our species had ever spoken across distances faster than a messenger could ride. That same person in middle age would have read in the newspaper about the first nuclear weapon in 1945. One life, one ordinary span from childhood to middle age, and in it, a civilization went from learning to be heard across the world to being able to end itself in an afternoon. The two capabilities did not arrive generations apart, giving the society time to absorb the first before facing the second. They arrived inside one person's memory. The same individual could remember both the wonder of the first broadcast and the dread of the first bomb. That compression, that closeness, is the whole of Sagan's worry made into a single human story, and it is why he set the number so low. Here is the pattern that worried Sagan, laid out plainly. We started broadcasting radio around the year 1900. Within a few decades, by 1945, we had built and used a weapon capable, in sufficient numbers, of ending our own civilization. 45 years. That is the gap for us between becoming detectable and becoming capable of self-destruction. A single human lifetime. A person born when the first voices crackled over the radio could have lived to see the first mushroom cloud. The window in which a civilization becomes loud and the window in which it becomes able to kill itself did not open centuries apart. They opened in the same breath. And when you ask why that would be, the answer is uncomfortable, because it suggests the link is not an accident. The thing that makes a civilization detectable is mastery of energy and matter. To send a signal across light years, you have to harness serious power, manipulate electricity, build transmitters, command the kind of energy that announces your presence to the universe. But that same mastery, the same understanding of energy and matter that lets you broadcast, is the understanding that lets you build weapons of enormous destructive power. The knowledge that makes you loud and the knowledge that makes you dangerous are not two different things that happen to arrive together. They are the same knowledge. You cannot get one without moving toward the other. Becoming audible to the universe and becoming capable of destroying yourself may be two sides of a single step. The analogy I keep coming back to is handing a toddler a sharp knife the same day they learn to walk. The problem is not that the child is bad. The problem is that two capabilities arrive at the same moment: mobility and access to something dangerous, and the wisdom to handle the second has not had any time to develop, because the very same growth that delivered the danger is what delivered the reach. A civilization in its first century of being loud is exactly that toddler. It has just acquired world-altering power, and it has had essentially no time to develop the maturity to handle it, because the power and the reach came in the same instant of growing up. Sagan looked at that and set L to 100 years, which is to say he suspected most civilizations do not survive their own adolescence, and notice that the knife in the toddler's hand is not specifically a nuclear knife, that is just the one we happen to forge first. The deeper worry is that any civilization, as it masters energy and matter, keeps being handed new knives, each one sharper than the last, on roughly the same schedule as it gains the reach to be heard. We made nuclear weapons, but the same growth in capability brings the power to alter a planet's climate, to engineer living things, to build machines that act on their own. Each of these a fresh way a civilization might end itself, each arriving before the wisdom to handle it has had time to grow. So the toddler does not just get one knife on the day it learns to walk, it gets a new and sharper one every few steps, for as long as it keeps growing. And the question of survival is whether judgment can ever catch up to a stream of dangers that keeps accelerating. That is the self-destruction hypothesis in its strongest form. Not one bad invention, but a permanent and widening gap between what a civilization can do and what it is wise enough to survive doing. There is a useful contrast hiding in the difference between a species and a civilization, and it cuts in an unexpected direction. The typical lifespan of a mammal species, before it goes extinct or changes into something else, runs to a few million years. So as a biological species, we might naively expect a long run, But a civilization is not a species. A civilization is a particular arrangement of a species, its institutions and knowledge and technology and social order, and that arrangement is far more fragile than the creatures that make it up. The humans could persist for ages while the civilization, the loud, technological, organized thing, comes and goes, or collapses, or transforms into something unrecognizable. Shermer's 420-year figure is about civilizations in that fragile sense, the named orders we can count in the history books, and they are brief precisely because they are arrangements, not organisms. This matters for L because the thing that has to last for the galaxy to be full of voices is not the species which might endure, but the loud technological arrangement, which history suggests is the most perishable form a species can take. The creatures may be durable, the civilizations they build appear not to be. There is a second, quieter estimate that points the same direction, and it does not even need nuclear weapons to make its case. The historian and writer Michael Shermer tried to put a number on L using human history itself by taking 60 actual civilizations from the historical record, the ones we have names and dates for, and averaging how long each of them lasted as a coherent civilization. The number he got was about 420 years. Now those were not technological civilizations in the radio sending sense, and the comparison is rough, but the point survives the roughness. Civilizations, the human ones we can actually count, tend to last centuries, not millions of years. They rise, they cohere for a while, and they come apart. If that is the natural rhythm of the thing, then a civilization staying not just intact but technologically capable and loud for millions of years would be wildly unlike anything in the only history book we have. It is worth pausing on how close the one example we have actually came, because it is the only real evidence the self-destruction hypothesis has, and it is sobering. In the decades after we built these weapons, there were moments, more than one, when the whole thing nearly went over the edge by accident or by misreading. A handful of times during the tensest stretches of the 20th century, early warning systems reported incoming attacks that turned out to be flocks of birds, or the moon rising, or a training tape left running, or sunlight glinting off clouds, and the only thing standing between those false alarms and a real exchange was a single human being deciding, on their own judgment, not to pass the warning up the chain. We do not need to dramatize this. The plain fact is enough. A civilization in its first century of being able to end itself spent that century repeatedly within one decision of doing so, and survived several of those moments not by design, but by the nerve of individual people. That is the one data point we have about how a young, loud civilization handles the power to self-destruct, and it is not a reassuring one. It is not proof we are doomed, but it is not nothing either. I want to be honest about how thin this reasoning is though, because honesty about the uncertainty is the whole point of doing this carefully. Everything I have just said is extrapolated from a single case, ours. We have not actually destroyed ourselves. The self-destruction hypothesis is not an observed law of nature. It is a fear, a pattern noticed in one example that has not even finished playing out. We came close, arguably, more than once in the 20th century, but close is not the same as proof that self-destruction is the rule. It is entirely possible that the danger of those first decades is a phase a civilization passes through and out the other side of, that the toddler grows up. We genuinely do not know. We are one child, still holding the knife, and we have not yet found out whether we are the kind of creature that puts it down. There is a deeper version of the worry that I want to name, because it is not really about weapons at all. It is about speed. The trouble with a technological civilization is that its power grows on one timescale and its wisdom grows on another, and the two are wildly mismatched. Technological power can grow explosively, doubling and redoubling in decades, because knowledge builds on knowledge and the tools improve the tools. But wisdom, judgment, the social and moral capacity to handle power, seems to grow much more slowly on the timescale of generations and institutions and hard-learned lessons. So a civilization that gains world-ending power in a single century has, almost by definition, not had time to grow the wisdom to wield it, because wisdom cannot be rushed the way technology can. The gap between how fast you can become powerful and how fast you can become wise enough to survive that power may be the most dangerous feature of the whole transition, and it would apply to anyone. Any civilization that discovers that knowledge compounds faster than judgment would face the same lethal mismatch, the same window where it is far more capable than it is careful. So self-destruction is the obvious answer to why L might be small, and it might be right. But I think it might also be too obvious and too human, too much about our particular weapons and our particular politics. It imagines the ending as a choice, a mistake, something a wiser civilization might simply avoid. And that raises a darker possibility, the one that actually unsettles me more. What if the limit on L is not a mistake a civilization makes, not a choice at all, but a trap built into the very act of becoming powerful? What if the thing that ends civilizations is not war, but something that happens to everyone who succeeds, for reasons that have nothing to do with wisdom? The astrophysicist Adam Frank has spent years on a question that sounds strange at first and then will not let go of you. What if what we call the Anthropocene, this moment where a civilization starts altering its own planet by using energy at a large enough scale, is not a specifically human failing at all, but a generic feature of any technological species anywhere in the universe? Not a mistake we made because of our particular greed or our particular politics, but a phase that anyone hits on any planet the moment they get powerful enough. If that is true, it changes the whole shape of the fear, because it moves the limit on L from something we might choose to avoid to something built into the physics of success. Start with the assumption almost all of us carry without noticing it. When we think about climate change, about resource depletion, about a civilization straining the planet that holds it, we think of it as our screw-up, a failure of our institutions, our short-sightedness, our specific kind of foolishness. And there is truth in that. But Frank's argument is that underneath the human specifics, there is something far more general going on, something that would apply to any civilization made of any kind of creature on any kind of world. And the root of it is not psychology, it is thermodynamics. Here is the generic part, and it is unavoidable. Any civilization that becomes powerful does so by using energy to do work. That is what a civilization is, in the most stripped-down physical sense, a system that captures energy and uses it to build and grow and maintain itself. But the laws of physics are strict about energy. When you use energy to do work, you do not get to use it cleanly and walk away. You necessarily produce waste, disorder, what physicists call entropy, and on a planet that waste does not vanish. It goes into the air, the water, the temperature of the world itself. The very act of using energy at the scale required to build a loud civilization changes the planet that civilization depends on. This is not a human flaw. It is what using energy means for anyone, anywhere. A civilization of intelligent machines, a civilization of creatures nothing like us, would face the identical bind because it is a feature of energy in planets, not of biology or character. I want to make the thermodynamic point concrete because it is the part that lifts this out of human politics and into something universal. Every time you use energy to do work, some of that energy is lost as heat, and that is not a flaw in the machine. It is a law, one of the deepest laws there is. You can build a better engine, but you cannot build one that escapes this, because the loss of usable energy to disorder is built into the structure of physics itself. Now scale that up to a whole civilization. A civilization is, physically, an engine running on a planet, taking in energy and using it to build and grow, and necessarily, unavoidably, dumping disorder and waste heat back into its world as it does. The more powerful the civilization, the more energy it commands, the more it must dump. And a planet is a closed enough system that the dumping accumulates, changes the chemistry of the air, the temperature, the balance of the whole. This is why Frank argues it is generic. It does not depend on the civilization being capitalist or greedy or short-sighted. It depends only on the civilization using large amounts of energy on a planet, which is the one thing every loud civilization, by definition, must do. The trap is not in our nature, it is in the thermodynamics of being a powerful thing on a finite world. There is a way to test this idea, at least in the limited way we can test anything about civilizations we have never seen. You treat a civilization and its planet not as two separate things but as one coupled system, where the civilization grows by consuming resources and the consumption feeds back onto the planet, changing its conditions, which then feeds back onto the civilization. The astrophysicist Adam Frank and his colleagues did exactly this a few years ago, and then ran it forward across a whole range of starting conditions, many different kinds of civilization on many different kinds of world, to see what tended to happen. In effect, they were asking what fates are common across all the ways a technological world might rise and use the energy of the planet beneath it. What it turns up is the part that stays with me. The fates sort themselves into a few broad shapes. In some runs, the civilization grows, strains its planet, and then manages a soft landing, leveling off into a sustainable steady state, a stable long-term balance with the world that holds it. Good, that is survival. But in many other runs, the civilization grows fast, overshoots what the planet can sustain, and then suffers a sharp die-off, the population crashing hard after the peak, as the degraded planet can no longer support what was built. And in a third kind of run, the worst kind, the civilization grows, triggers changes in the planet that feed back faster and harder than it can adapt to, and collapses all the way towards zero, a full collapse, with no one left. Same basic setup, different parameters, wildly different fates, and a great many of them end badly, not because anyone in the model was wicked, but because the coupled system of civilization and planet is genuinely hard to steer through the transition without crashing. This connects to an idea you may have heard, the Great Filter. The Great Filter is the proposal that somewhere on the long road from lifeless matter to a lasting, galaxy-spanning civilization, there is at least one step so hard that almost nothing gets past it, and that this nearly impassable step is what keeps the galaxy silent. People usually argue about where the filter is. Is it behind us, in the origin of life, or the leap to complex cells, which would mean we are rare survivors? Or is it ahead of us, waiting? And what the L term suggests, what this whole video suggests, is that the filter might be exactly here, at the lifetime of technological civilizations, not in getting started, which the universe may do easily, but in lasting, which it may almost never manage. If L is the filter, then the hard step is not behind us. It is the one we are standing in the middle of right now, the transition from a young, loud civilization to an old, surviving one, and the silence is the sound of almost everyone failing it. That is the darkest place the idea goes, and it is why L and the Great Filter are really the same fear, wearing two different names. That is what I mean by a generic bottleneck. The danger is not a villain. There is no war in these models, no bomb, no cruelty. There is just a civilization doing the thing all civilizations do, growing and using energy, and discovering that the planet pushes back, and that steering through the moment when it pushes back is a narrow and difficult passage that many trajectories simply do not survive. It is the same arc as a gold rush town, in a way. A settlement booms on a single rich resource, grows fast and wild around it, and then when the resource runs thin or the ground is poisoned by the taking of it, the boom becomes a bust and the town empties. The same curve, over and over, in mining towns across the world, not because the people were uniquely foolish, but because the dynamics of booming on a resource carry the bust inside them. Frank's argument is that a technological civilization on a planet may follow that same curve, and that the curve may be written into the physics, not the character. It helps to be clear about what a model like this is actually for, because people often misunderstand it in both directions. A model like Frank's is not a crystal ball. It cannot tell you what will happen to any real civilization, including ours, because it does not contain the real numbers, the true strengths of the feedbacks, the actual choices a civilization might make. Anyone who points at one of these runs and says, "This is our future," has misunderstood it. But a model is also not worthless just because its numbers are invented. What a good model does is show you the shape of the possibilities, the kinds of outcomes the basic dynamics allow, the way the pieces can fit together. It is closer to a wind tunnel than a weather forecast. A wind tunnel does not tell you whether it will be windy on Tuesday, but it tells you, reliably, how air behaves around a wing, which is a real and useful thing to know. Frank's models are a wind tunnel for civilizations. They do not predict our weather. They show us how the air moves around the wing of a planet carrying a growing technological civilization. And what they show is that collapse is an easy and natural flow, the kind of thing the dynamics produce without anyone steering toward it. That is worth knowing, even though, maybe especially because, it is not a prophecy. Now I have to be straight with you about what these models are and are not, because it matters, and because papering over it would be exactly the kind of thing this channel does not do. These are simplified models with parameters we essentially made up, because we have no real data on alien civilizations to feed them. They are not predictions. Critics point this out, correctly, that you can get a model to do almost anything, depending on the numbers you put in, and we do not know the real numbers. So Frank's models do not prove that civilizations collapse. What they do, and this is still valuable, is show that collapse is a natural and common outcome of the basic dynamics, the kind of thing that falls out of the equations easily, for generic reasons, without anyone having to be evil or stupid. They turn self-destruction from a specifically human moral failure into something closer to a physical tendency. And that is darker, because you cannot fix a physical tendency by simply being wiser than the last civilization. So now we have two reasons L might be small. It might be small because power is dangerous and civilizations destroy themselves, or it might be small because growth on a planet is self-limiting and civilizations collapse under their own success. Both are real possibilities, but notice that both are still, in the end, guesses, reasoned from models and from our single example. So let me ask the question a scientist has to ask: is there any actual evidence, anything we can point to out in the universe, that bears on how long civilizations really last? And it turns out there is one piece of evidence, enormous and strange, that we have been sitting inside this whole time: the silence. Here is a fact about ourselves that almost nobody stops to feel. We have been loud for about 100 years, and we are already getting quieter. The window in which a civilization can be heard might be far narrower than the window in which it exists, and we are the proof, because our own loud window may already be starting to close only a century after it opened. There is an image people love about this, and it is half true, which makes it worth correcting carefully. The image is that all our old broadcasts, the first radio plays, the early television, are still out there, racing outward in an ever-growing bubble, so that an alien astronomer at the right distance could be watching our oldest programs right now. The bubble is real. Our radio leakage has been expanding outward at the speed of light for about a century, so it now reaches roughly 100 light years in every direction. A sphere of human noise a couple hundred light years across. But here is the correction, and it is the part that matters for L. That signal does not stay strong. It spreads out as it travels, and it gets fainter with distance, fainter and fainter, until it sinks below the natural radio hiss of the galaxy itself and becomes, for any realistic receiver, undetectable. The honest estimates are that our ordinary leakage would be extremely hard to detect from more than a few light years away, even with enormous instruments. So the bubble is not a clear broadcast filling space. It is a faint ripple, fading as it goes, already washed out into the background not far past our nearest neighbours. The flare is even dimmer and more local than the romantic version suggests. Think about how we became detectable in the first place. In the early and middle 20th century, we broadcast radio and television by blasting powerful signals out from tall towers in all directions, and a great deal of that energy leaked past the horizon and out into space, radiating outward as a steadily expanding shell of human noise. For a few decades, Earth was genuinely loud in radio, a planet spilling its signals into the dark. That was the flare. That was our match catching. But look at what is happening now. We are moving fast away from exactly the kind of broadcasting that leaks. Signals travel through cables now, through fiber, contained, not radiated. Satellites beam tightly focused downward at the planet, rather than spilling outward. Our communications are becoming more efficient, more targeted, more digital, which from a distance means quieter. The very same technological progress that made us loud is now making us harder to hear, because a civilization that has gotten good at communication wastes very little of its signal into space. So our detectable phase, the part of our existence where someone across the dark could pick us up by our leakage, may turn out to be a brief few decades in the middle of the 20th century and tapering after, rather than a permanent feature of our existence, a flare, not a steady glow. And if that is true of us, it may be true generally. A civilization might be loud and detectable for only a thin slice of its total lifetime, the awkward adolescent window after it learns to broadcast, but before it learns to do so efficiently, which means that even counting how long civilizations are detectable might badly undercount how long they exist. The match might keep burning long after the brightest flare has passed, just too dim for anyone to see. People have actually tried to turn our silence into a number for L, which is a strange and clever thing to do, and the number is sobering. The reasoning runs like this. If you assume the galaxy reliably produces technological civilizations on some fraction of its habitable worlds, then the number that are detectable right now depends directly on how long each stays detectable. And since we have looked and found none nearby, you can work backward to put a ceiling on how long the typical detectable lifetime can be, because if it were long, there should be enough of them lit at once that we would likely have heard one by now. A recent analysis along these lines concluded that, given our lack of detections, the mean lifetime of detectable civilizations is likely under about 5,000 years. Now that number rests on assumptions you can argue with about how common civilizations are to begin with, and I would not treat it as gospel. But notice what it is doing. It is using the silence, the one piece of data we have, to estimate the very term Sagan said was the most important and the least knowable. And the estimate it lands on is short. Not 100 years, but not the comfortable millions either. A few thousand years, the span of recorded human history, and then dark. Now set that against the age of the galaxy, because that is where it becomes vertiginous. The galaxy is more than 13 billion years old. Take a civilization that stays detectable not for decades, but for a generous 10,000 years, far longer than our loud window looks like it will be. 10,000 years sounds like a long time, longer than all of recorded human history. And against 13 billion years, it is nothing. It is a flash. If you compress the whole history of the galaxy into a single year, a civilization detectable for 10,000 years would be visible for about 20 seconds of that entire year. Strike a match, let it flare for an instant, and that instant is the civilization's entire loud life against the long dark night of the galaxy's history. There is a second way to feel the brevity, and it comes from a stadium. Picture a packed stadium at night, tens of thousands of people, and somewhere in the crowd a single camera flash goes off, a bright pop gone in a fraction of a second. If you happen to be looking at exactly that spot at exactly that instant, you saw it, blinding and clear. But look away for even a moment and you would never know it happened. Now imagine you are trying to prove the stadium is full of people by catching their flashes, except each person flashes once, randomly, across an entire night. At any given glance, you might see one or none, even though the stadium is packed. The darkness of the stands between flashes is not evidence the seats are empty. It is just evidence that each flash is brief and they are not synchronized. A galaxy of brief civilizations is that stadium. The flashes are real, the seats are full, and yet almost every time you look, you see the dark. Because a flash is a moment and the night is long. This is the second time the match has come up, and now it earns its real meaning. So let me say it plainly. The flare is the easy part. Getting the match to light, going from a planet to a civilization that can broadcast, as hard as that is, as many front-end factors as it requires, is the part that somewhere across hundreds of billions of stars and 13 billion years probably happens reasonably often. Every match lights, given enough matches and enough strikes. The terror is not in the lighting. The terror is in how fast the thing burns down. The brevity is the whole problem. A civilization could be common as striking a match and still leave the galaxy dark if the flame never lasts. I do have to draw one careful distinction here, because it is easy to blur, and the blur would be dishonest. Being detectable and being alive are not the same thing. Everything I just said is about the loud window, the time a civilization can be heard. A civilization could go quiet, stop leaking signals, become efficient and contained, and still be perfectly alive and thriving for ages afterward, just silent. So a short detectable window does not by itself prove a short lifespan, it only proves a short flare. The match could go dark to our instruments and the civilization behind it could live on. In fact, the better a civilization gets at everything, the quieter it likely becomes, because waste and leakage are inefficiency, and a mature civilization wastes little. So there may be a cruel rule hidden here, that the most successful civilizations are the hardest to detect, their very competence making them silent. If that is so, then our searches are biased toward catching civilizations exactly like us, young and loud and wasteful, in the brief clumsy window before they either die or learn to be quiet. We may be best at detecting the ones most like us, which is to say, the ones in the most dangerous part of their lives. That is real, and I will not pretend the silence directly measures survival, but here is why it still matters enormously, and why it is the best evidence we have. Because whether civilizations go dark by dying, or go dark by going quiet, the result for anyone listening is the same. A galaxy that sounds empty, and that silence is the one piece of actual data we have about the world beyond us. So let us take the silence seriously, as evidence, and ask what it is actually telling us. Because we have been listening hard for a long time now, and what we have heard is nothing at all. More than 60 years ago, for the first time, we aimed a radio dish at two nearby stars, Tau Ceti and Epsilon Eridani, and listened. Two ordinary stars, a dozen or so light years out, close enough to be worth a try. We were listening for a signal, any signal, a pattern in the radio noise coming off those stars that could only have been made by a mind. It was the first time we had ever seriously, systematically pointed at another star and asked if anyone was there, and what came back was nothing. Static, the ordinary hiss of the universe pouring out of the dark around those two stars, and no voice anywhere in it. That first careful nothing was the beginning of one of the strangest records we have ever kept, the record of our listening and of the silence that has answered every single time. I have to be fair about one thing before I lean on the silence too hard, because it cuts against my own argument and you deserve to hear it. The search, as enormous as it sounds, has actually covered very little. There is a well-known way of putting this. If you think of the full search space of SETI, all the stars, all the frequencies, all the times you would have to listen, all the kinds of signal you would have to look for, as an ocean, then everything we have searched in 60 years amounts to about a single glass of water dipped out of that ocean. One glass. So when I say we have heard nothing, I do not want to pretend we have combed the galaxy and found it empty. We have sampled a tiny corner of the possibilities. A confident person could say we have barely begun to look, and they would be right. The silence is real, but it is the silence of having dipped one glass, not of having drained the sea. I hold the silence as evidence, but I hold it loosely, and so should you. because we did not stop with 2 stars. In the 60-some years since Project Ozma, we have listened with growing power and growing sophistication, with bigger dishes and better receivers, scanning more stars across more frequencies for more hours. Programs have surveyed thousands of nearby stars. More recent efforts have swept across billions of stars in the plane of the galaxy. We have looked for narrow radio signals, for pulses of laser light, for the heat that enormous alien engineering would give off, for the chemical traces of industry in distant atmospheres. And after all of it, the confirmed tally of signals from another civilization stands at exactly 0. Not a single confirmed voice. The sky, as far as we have been able to hear, is silent. Now, I have to be careful here, because silence is slippery evidence, and it is easy to overclaim it. The silence is not proof that we are alone. It absolutely is not. But here is the thing I want you to sit with. The silence is not nothing either. It is real information. An absence can be a finding. When a doctor looks at a scan and does not see a shadow that should be there if a certain disease were present, that absence is data. It tells them something real about what is and is not going on, even though it is the absence of a thing rather than the presence of one. Our decades of silence are like that. They are an absence that constrains the possibilities. The trick, the thing that separates a useful absence from a meaningless one, is knowing what you would have expected to see if a thing were true. The doctor's empty scan is informative only because they know what the disease would have looked like on it. And the silence of the sky is informative in the same way, but only to the degree that we know what a galaxy full of long-lived civilizations should sound like. That is why all the careful work on what a real techno-signature would look like matters so much. The better we understand what we should be hearing if the optimistic picture were true, the more the continued silence actually weighs. An absence is only as informative as your knowledge of what the presence would have been, and on that front, slowly we are getting better, which means the silence is slowly getting louder. They are the universe declining so far to show us the one thing we most want to see, and that declining is itself a clue. I want to defend the idea that an absence can be real evidence because people are often too quick to wave the silence away as proving nothing, and that is not quite right either. Think about how much of medicine works on exactly this principle. A doctor orders a scan looking for something specific, and when the scan comes back clear, that clear result is not nothing, it is a finding. It rules things out, it changes what the doctor believes and what they do next. An absence in the right context where you genuinely would have seen the thing if it were there, carries real information. The trick is the phrase where you genuinely would have seen it. An absence is only evidence to the degree that you actually looked in the right place with enough sensitivity to have caught the thing. And that is exactly the tension in our silence. In the directions and frequencies and times we have genuinely searched with enough power, the silence is real evidence, it does constrain, but we have searched so little of the whole space that the constraint is weak. So the honest position is the careful middle one. The silence is data, not nothing, but it is thin data, a clear result from a scan that has so far only covered a small patch of the body. It tells us something. It does not yet tell us much. So what does the silence actually constrain? Think back to the equation, to the 2 ways you could end up with a silent galaxy. One way is that the front-end factors are tiny, that life or intelligence or technology is just incredibly rare, so that almost no civilizations ever arise in the first place. That is the lonely answer, the we are nearly unique answer. But there is a second way to get the exact same silence, and it does not require life to be rare at all. You can have a galaxy that easily and frequently makes life, makes intelligence, makes technological civilizations, matches striking all over the place across the eons, and still get total silence if L is small, if the civilizations do not last, because then at any given moment almost none of them are lit, and the odds that one is both close enough and loud at the same time as us drop to almost nothing. And that second answer, I think, is the one too few people sit with, because it is in some ways the more haunting of the two. We tend to hear the silence and reach for one of two comforting stories. Either we are special, the rare ones, almost alone, which flatters us, or we tell ourselves we just have not looked hard enough yet, that the signal is out there and we will find it next year, which reassures us. But the silence is equally consistent with a third story that is neither flattering nor reassuring. A galaxy that is, or was, full of life, full of civilizations, full of minds that looked up and wondered exactly as we do, and that we hear nothing from, not because they were never there, but because they do not last, because the matches keep going out, because L is small. I want to stay with that image for a moment, because it captures something the cheerful and the gloomy readings both miss. We argue about whether the galaxy is empty or full, as if those were the only options, and as if they would look different, but a graveyard is full. It is densely, achingly full, more full of the people who once lived than any living town is, and it is completely silent. Fullness and silence are not opposites there, they are the same place. If civilizations are common but brief, then the galaxy is not an empty field, and it is not a crowded city. It is a graveyard, crowded with the traces of the dead, dense with everyone who came before, and silent for exactly that reason, because the crowd is a crowd of the gone. And the strange part is that we would not be able to tell that graveyard from an empty meadow by listening, because both make no sound. The only difference is what is under the surface, and we cannot see under the surface from here. We can only hear the silence on top, which the full graveyard and the empty field share. A crowded graveyard sounds exactly the same as an empty field. Both are silent, and from where we stand, with the instruments we have, we cannot yet tell which one we are listening to. This whole problem, the gap between how full the galaxy seems like it should be and how silent it actually is, has a name. It is called the Fermi paradox, after the physicist Enrico Fermi, who is supposed to have cut through a lunchtime conversation about aliens with a simple question: where is everybody? If the galaxy is old and large and friendly to life, it should have filled with civilizations long ago, some of them far older than us, and we should see signs of them everywhere, and we do not. That is the paradox. And over the years people have proposed dozens of solutions to it, whole books of them, but they sort, roughly, into two families. Either the civilizations were never there, because the front end is hard and life or intelligence is rare, or they were there and we cannot see them for some reason. And a small L is the cleanest member of that second family, because it does not require life to be rare, and it does not require any exotic explanation for the silence. It just says they were here, and they did not last, and so they are not here now. Of all the answers to where is everybody, the one this video defends is the bluntest. They were here. They are gone. They keep being gone. That is the cleanest way to state what the silence permits. A short L is the single simplest change you can make to the whole picture that turns a life-rich galaxy into a silent one. You do not have to assume life is rare. You do not have to assume intelligence is a fluke. You can keep all the front-end factors generous, a galaxy that loves to make minds, and still get our silent sky, with one adjustment. Make the civilizations brief. That is it. That one move does all the work, which is why the silence, slippery as it is, points a quiet finger at L, at the lifetime, at the very term the equation already told us was the one that mattered most. I want to be fully honest about the other explanations, because they are real, and I am not going to wave them away to make my argument cleaner. The silence could mean civilizations are out there but choose to stay quiet, listening rather than broadcasting, hiding on purpose. It could mean they are using some technology to communicate that we do not even know to look for, talking past us in a medium we have not discovered. It could mean they are simply farther apart or fainter than our instruments can yet reach, and we have only searched a tiny fraction of the haystack. Every one of those is possible, and every one would also produce silence. So the silence does not prove a short L, but of all the explanations, A short L is the one that requires the fewest special assumptions, the one that fits most naturally with everything else we have said about self-destruction and bottlenecks and the brevity of the flare. It is not the only reading, it is the most economical one. So let me try to show you what that economical, haunting reading actually looks like when you picture not one star or two, but the whole galaxy across the whole of time at once. Because that picture is the most vertiginous thing in this entire video, and once you see it, the silence never sounds the same again. Picture a dark room the size of the galaxy. In it, a few 100 billion matchboxes, one for roughly every star. And picture time, not as the present moment, but as a whole long night, 13 billion years of it, running from the early galaxy to now. Now watch what happens across that night if civilizations are brief. Here and there, at random, a match is struck. It flares bright and clear for its little span, and then it burns down and goes dark. Somewhere else, later, another is struck, flares and dies, and another. Across the whole enormous night, matches are being lit and going out, one after another, scattered through the dark. But here is the thing. If each flare lasts only a moment against the length of the night, then almost never are two of them burning at the same time. The everyday version of this that I find clearest is a field of fireflies on a summer night. Imagine a wide field, and it is full of fireflies, thousands of them, genuinely full. But each firefly blinks only for a moment, and then stays dark for a long while. And they are not synchronized, each one blinking on its own schedule. Now stand at the edge of that field and take a single photograph, one instant frozen. In that photo, you might catch 2 or 3 points of light, or none, scattered across a darkness that looks almost empty. Someone looking only at your photograph would swear the field was nearly deserted, but the field is teeming. The darkness in the photo is not absence, it is just that, at any single instant, almost all the fireflies happen to be in their dark phase, and only a scattered few are mid-blink. The galaxy, under a small L, is that field, and our entire existence as listeners, these few decades, is the single photograph. We are looking at one frozen instant of a field that may have been blinking with civilizations for billions of years, and concluding, from the dark in our one snapshot, that the field is empty. It may simply be that we caught it between blinks. And here is the part that makes the field stranger than any field on Earth, because of the one thing light does. When you look out across the galaxy, you are never seeing it as it is now. You are seeing each point as it was when its light left, and that light has been crossing the dark for hundreds, thousands, tens of thousands of years to reach you. Look toward the center of the galaxy, and you are seeing stars as they were when the first cities were being built on Earth. Look at the far edge of the disk, and you are seeing light that left before our species had a written language. So the single photograph we take is not even a photograph of one instant. It is a smear of 100,000 different moments, each star showing us a different page of its past, all of it arriving at once and pretending to be the present. A civilization could be blazing away with signals right now, this very moment, around a star on the far side of the disk, and its light simply has not reached us yet, and will not for another 50,000 years. The dark we see is not even the dark as it is. It is the dark as it was, layered over itself, every layer a different age of the galaxy, and somewhere inside those layers the blinks may be happening constantly, just not in any moment we are able to see. We are not only looking between the blinks in space, we are looking between them in time, at a picture so old in its farthest corners that whole civilizations could have risen and gone dark in the gap between when their light left and when it lands on us. That is the picture I want you to hold, because it is the heart of everything. We tend to imagine the question of alien civilizations as a question about space. Are they out there, somewhere, across the distance? But if L is small, the real scattering is not across space, it is across time. The civilizations are separated from each other, not mainly by light years, but by epochs, by the eras of galactic history they happen to fall in. One flares and dies a billion years before another is even struck. They are contemporaries of nothing. Each one looks out during its brief moment, sees a dark room, and concludes it is alone, and in the only sense that matters for contact, it is because the others are scattered up and down a timeline it can never reach. There is a way to feel this that I find almost unbearable in the right way, by squeezing the whole history of the galaxy into a single calendar year. Let the formation of the galaxy be the first instant of January, and now be the last instant of December. On that scale, all of recorded human history, every empire and every name we know, fits into the final fraction of the last second before midnight. And a civilization that stays detectable for 10,000 years, far longer than our flare looks likely to be, would be lit for about 20 seconds out of the entire year. 20 seconds, somewhere in 365 days. Now scatter a few thousand such civilizations at random through the year, each lit for its 20 seconds. Ask yourself how often two of them would be glowing at the same instant. Almost never. You could run that calendar over and over and find, most moments you checked, that nothing at all was lit. And on the rare occasion something was, it was alone. That is not an empty year. Things happened all through it. It is a year so long and the flares so brief that the lit moments almost never coincide. We are checking the calendar at one instant, our instant, and finding the dark between the sparks. Let me put the numbers to it, because the numbers are what make it land rather than just sound poetic. The galaxy is more than 13 billion years old. Suppose a civilization stays detectable for, generously, 10,000 years. Then the fraction of galactic history during which that one civilization is lit is 10,000 divided by 13 billion, which is less than 1 in a million, less than 1 part in a million of the whole night. That single match is burning. So even if the galaxy produced 1,000 civilizations, or 10,000, or 1,000,000 of them scattered randomly across all that time, the chance that any two happen to overlap, happen to be lit in the same narrow window, is small. You could have a galaxy that has produced millions of civilizations over its history and still find at any given instant that almost none are burning at once, crowded across time, empty at any moment. That is not a contradiction. That is just what brevity does to a long enough night. I want to sit with the strangeness of being separated by time rather than space, because it is a kind of distance we do not have good instincts for. We understand spatial distance. Someone is far away, and if you travelled far enough, you could reach them. It is hard, maybe impossible, at these scales, but it is the kind of barrier the mind can picture. Distance in time is different and worse because it is absolute. If a civilization flourished in our galaxy 1 billion years ago and went dark, there is no speed, no technology, no patience that lets you reach them because they are not anywhere. They are not far away. They are over. You cannot travel to a time. And the same is true in the other direction, of the civilizations that will arise long after we are gone, who might wonder about us exactly as we wonder about whoever came before, and who will find the same silence because by their moment our match will have long since burned out. We are not just possibly alone in space. We may be sealed into our own slice of time, with neighbours on both sides of us, before and after, none of whom we can ever touch, because the one direction nothing travels is across the years. That is a loneliness with no remedy, even in principle, and it is the one a small L would impose on everyone, forever. And that, I think, is the most unsettling resolution of the silence, more unsettling than being alone. Because being alone, being the only match ever struck, at least has a kind of bleak dignity to it, a uniqueness. This is worse. This is a universe that is not empty at all. It is a universe that has been making minds, making civilizations, making creatures that look up and wonder and reach out over and over for billions of years. It is just that they are spread so thin across time that they amount functionally to solitude. Company that exists, that genuinely exists, but never when you do. The loneliness of the asynchronous. Not no one ever, but no one now. No one you could ever reach, because the ones like you are separated from you by the one distance nothing can cross, which is time. And I want you to hold what each of those flares actually was, because it is easy to let them blur into abstract points of light. Every one of those brief matches, if the picture is right, was a whole world that woke up. A planet where life crawled out of its chemistry and spent billions of years becoming something that could look up. A species that learned to speak, that built things, that loved and argued and wondered, that turned its instruments to the sky and asked the exact question we are asking tonight. Am I alone? Each flare was someone's entire history, their art and their science and their long, slow climb to the moment they could be heard, compressed into a spark that flared and went dark before the next one was struck. The galaxy, under this picture, is not just scattered with brief signals, it is scattered with finished stories, each one complete, each one having felt to those inside it like the center of everything, the way ours feels to us. That is what the silence is full of, if it is full of anything. Not noise, lives, whole histories that ran their course in the dark between our listening and that we will never hear because the one thing none of them could do was last long enough to overlap with us. There is a gentler image for the same idea, and I reach for it because the Matchbox version can feel too bleak to hold, and this one is truer to how it actually works. Picture a summer field at dusk, full of fireflies. Each firefly blinks for only a moment, then goes dark, then another blinks somewhere else. If you photograph the field with a fast shutter, catching only a single instant, you might see one or two lights, or none, against a field of black, and you could be forgiven for thinking the field was nearly empty. But leave the shutter open for an hour, and the photograph fills with light, hundreds of trails crossing everywhere, because the field was full the whole time. The fireflies were just never all lit at once. The galaxy, under a small L, is that field, and we are the fast shutter, catching a single instant. We see the dark between the few lights, and read it as emptiness, but the long exposure, the one no one can take, the one that would gather all of cosmic history into a single image, might be full of light, crowded with brief blinks scattered across billions of years. The field is not empty. We are just looking with too fast a shutter at too short a moment to see that it was always full. This is the match at its full weight, so let me land it. The silence we hear when we point our telescopes at the dark is not the silence of an empty room. It is the silence of a room where the matches keep going out. 100 billion matchboxes, sparks struck all across the long night, brief flares of light and wonder and reaching, each one going dark before the next is lit. The room was never empty. It has been full of brief fires this whole time. We just live in the gaps between them, as every match does, as perhaps every match always has. There is a question I have been circling without landing on, because everything depends on it, and I wanted you to feel the weight of the silence first. We keep assuming civilizations die young, but has anything, anywhere, ever actually beaten this? Ever managed to last? I am going to come back to that, because the answer is not what either the optimists or the doomers want it to be. Hold on to it, because if even one kind of match can be made to burn through the whole night, then everything I have just shown you changes shape. Now to the question I held back. The honest answer is that we do not know if anything has ever lasted, and that is stranger than a yes or a no, because a civilization that truly endured would leave marks we could find, and we find none, which means either nothing has lasted, or the ones that did are so quiet we cannot tell. Survival, if it happens at all, leaves almost the same trace as never having been. Let me unfold that, because it is the genuine knife edge of this whole subject, and both sides of it are held by serious people. The core of the optimistic case is the idea of spreading out, of not keeping all your existence in one place. Almost everything that can end a civilization, the self-inflicted catastrophes, the planetary collapse, even the gamma ray bursts and the dying star, is local. It happens to a planet or a star system. So the argument goes that a civilization which spreads beyond a single world, which establishes itself around more than one star, becomes enormously harder to kill, because no single local catastrophe can reach all of it at once. A disaster that would end a one-planet civilization becomes, for a spread-out one, a tragedy in one place that the rest survives. And a civilization that survives long enough to spread that far would, the argument continues, keep spreading, becoming more distributed and more durable with time until it is nearly impossible to end, its existence backed up across so many places that nothing short of the death of the whole galaxy could finish it. That is the vision of a long L, and it is not foolish. It follows logically. If, and this is the enormous if, a civilization can survive long enough and cross enough of the dark to spread in the first place, the immunity comes after the spreading, and the spreading requires surviving the very bottleneck we are worried about and crossing the very distances we have found almost nothing can cross. On one side are thinkers like the paleontologist Peter Ward, who argue that the brevity is a phase, not a fate. The idea is that a civilization which makes it through its dangerous adolescence, through the nuclear century and the planetary bottleneck, would come out the other side enormously capable. It would spread its presence around, no longer dependent on a single planet or a single star. And a civilization like that, distributed and technologically mature, becomes nearly immune to the things that kill young civilizations. It could, on this view, last not thousands of years but millions, even billions. The match, once it survives its first gust of wind, might be able to burn almost indefinitely. If that is right, then L is not small for everyone. It is small for the young and enormous for the survivors, and the galaxy might hold a few ancient, enduring fires. To see why a long-lived civilization should be loud, it helps to know what physicists think a truly old one would look like. There is a way of ranking civilizations by how much energy they command, proposed by the astronomer Nikolai Kardashev. A civilization like ours, drawing on the energy available to a planet, is near the bottom. The next step up is a civilization that captures the entire energy output of its star, and the physicist Freeman Dyson pointed out the natural way to do that by building an enormous structure or swarm of collectors all the way around the star to catch its light. We call it a Dyson sphere, and the crucial thing for us is that such a structure could not hide. A star wrapped to capture its energy would still have to radiate that energy back out as waste heat, glowing in the infrared, so a Dyson sphere would show up as a strange star that gives off heat without the visible light it should have. This is one of the most searched for technosignatures precisely because it is so hard to conceal. Astronomers have combed survey data looking for exactly these infrared signatures, stars that look wrong in the way a wrapped star would. And the result, so far, is nothing clear. The very thing a long-lived, energy-hungry civilization would almost have to build is the thing we have looked for and not found. But here is the problem with that hopeful picture, and it is a serious one. If such long-lived, hugely capable civilizations existed, they should be the easiest thing in the universe to find. Think about it. A civilization that has lasted 1 million years, that has spread out and harnessed the energy of stars, would leave marks, enormous structures around stars to capture their energy. Persistent beacons deliberately broadcasting for the ages, the waste heat of titanic engineering glowing in the infrared. These are exactly the kind of long-lived, large-scale signatures that our searches are best at detecting, far easier to spot than the faint radio leakage of a young world like ours. A long-lived civilization is a lighthouse, sweeping its beam across the dark for age after age, and a lighthouse is built to be seen. And when we look for those lighthouses, we find none. No megastructures, no persistent beacons, no unmistakable waste heat of stellar-scale engineering. Nothing. And this is genuinely strange, so I want to dwell on it rather than rush past. Studies of what kinds of alien signatures we could actually detect have found something almost paradoxical. The signatures most likely to be found are the long-lived ones, the ones that persist for over 1 million years, precisely because something that lasts that long has so many chances to be noticed and sweeps across so much space and time. Researchers like Amedeo Balbi and Milan Cirkovic have made this point carefully. If long-lived technosignatures exist at all, they should dominate what we detect, because longevity is exactly what makes a signature findable. So the absence of any long-lived signature is not a small thing. It is the absence of exactly the thing we should most easily see if it were there. The lighthouse that should be impossible to miss is missing. There is one reading of the silence I have avoided until now, because it is the most unsettling and the least falsifiable. But honesty requires putting it on the table. It is the possibility that long-lived civilizations exist and are deliberately silent, not out of efficiency, but out of fear. The idea, sometimes called the dark forest, is that in a universe where you cannot know the intentions of anyone else, and where the distances mean you could never defend yourself in time, the safest thing any civilization can do is stay quiet and never reveal its position, treating the galaxy as a dark forest in which the wise predator and the wise prey alike make no sound. If that were true, then the silence would not mean civilizations are brief at all. It would mean the old ones learn to hide, that broadcasting, the very thing we did in our loud century, is a beginner's mistake that mature civilizations grow out of, and that the galaxy is full of listeners and empty of talkers. I do not know whether to believe this. It is unprovable almost by construction, and unprovable ideas deserve caution. But it sits there as a genuine alternative to a short L, a way the sky could be silent and full at the same time, and I would be hiding the ball if I did not name it. And I want to be clear about why this particular uncertainty matters so much for us, specifically sitting here at the start of our own loud window. If it turns out that nothing has ever lasted, that the bottleneck is a near-perfect filter, then we are almost certainly not the exception, and the honest expectation for our own future is grim. But if it turns out that some things have lasted, that a long L is achievable, and the survivors are simply quiet, then the bottleneck is passable, and the question becomes not whether survival is possible, but whether we will be among the ones who manage it. Those are very different worlds to be living in, and the maddening thing is that they look identical from where we stand. The same silence is the evidence for both. So we are in the position of a person who needs to know whether the thing ahead of them has ever been survived, and cannot find out, because the survivors and the dead have left the same empty record. We have to decide how to live inside a question we cannot yet answer, and that, it turns out, is the actual human situation, dressed up in starlight. So put the two halves together and feel the bind they create. Either nothing has ever lasted, no civilization anywhere has beaten the bottleneck and grown old, which would mean the brevity is close to universal, a near iron law, and that is the dark reading. Or some civilizations have lasted, have grown ancient and capable, but are for some reason invisible to us, silent by choice, or built in ways we cannot recognize, or deliberately hidden, which is its own unsettling thought, a universe of elders who have chosen not to be seen. Both readings are disturbing in different ways, and we cannot currently tell which one we are living in. That is the honest answer to the question I held back. Not yes, something lasted, not no, nothing did, but a genuine, vertiginous we cannot tell, where survival and absence leave nearly the same trace. The image I keep returning to for a long-lived civilization is a lighthouse. A lighthouse is built precisely to be seen, to throw its beam out across the dark for year after year, decade after decade, so that anyone who passes within range at any time will catch it. If the galaxy held civilizations that had lasted 1,000,000 years, they would be lighthouses, their presence sweeping across so much space and so much time that our chance of catching the beam, even in our brief glance, would be high, far higher than catching some young world's faint 100-year flicker. The whole logic of detection favors the long-lived, because longevity is what gives a signal the room to be found. So when we look across the dark and see no lighthouses, no steady ancient beacons, no beams that have been sweeping the coast for ages, that absence is louder than the absence of young flickers. It is the absence of exactly the thing built to be impossible to miss. A coast with no lighthouses is either a coast with no keepers, or a coast whose keepers have, for reasons of their own, chosen to let the lamps go dark. There is one more turn of the knife in this, and it follows from the silence we already discussed. A civilization that survives by growing quiet, by becoming efficient and contained, and no longer spilling its signals into the dark, would be invisible in exactly the same way a dead one is. We said earlier that going quiet and dying look the same from across the room. Here is the cost of that. It means survival itself, at least the mature, efficient, no longer wasteful kind of survival, might be nearly indistinguishable from extinction from the outside. The civilizations that made it might be the quietest of all, precisely because making it means no longer shouting into the void, which would mean the galaxy could be full of ancient survivors and full of the dead, and from where we sit, listening, the two would sound identical. So we do not know if a long L is possible. But suppose it is. Suppose a civilization could in principle last. What would actually be trying to stop it? Because even for the ones that beat themselves, the universe is not finished with them. Imagine a civilization that did everything right. It passed through its nuclear adolescence without ending itself. It navigated the planetary bottleneck, learned to use energy without wrecking the world that held it, found the soft landing into a sustainable, steady state. It survived itself, which we have been treating as the hard part. And now I have to tell you the thing that I find genuinely sobering, which is that surviving yourself is not the finish line. There is no finish line, because even a civilization that has beaten every danger it makes for itself still lives in a universe that, on long enough timescales, is actively trying to end it, for reasons that have nothing to do with the civilization at all. Start with the gamma ray burst, because it is the most frightening of these and the most indifferent. When certain massive stars die, or when certain dead stars collide, they release a burst of gamma radiation so concentrated that it is focused into narrow beams firing out from the poles, and these are the most energetic single events in the universe since the beginning. If one of these beams happened to be pointed at an inhabited planet, even from thousands of light years away, the consequences would be severe. The gamma rays would tear into the atmosphere and, in a matter of minutes, strip away much of the ozone layer, the thin shield that protects the surface from the killing ultraviolet light of the planet's own star. There is serious scientific argument from researchers like Adrian Malott and Brian Thomas that exactly this may have happened to Earth, that a gamma ray burst may have caused one of the great mass extinctions in our planet's deep past, the one at the end of the Ordovician period, hundreds of millions of years ago, a beam fired from a dying star half a galaxy away, arriving without warning, at the speed of light, with nothing that could be done. What unsettles me about these threats is their total indifference. A self-inflicted catastrophe, however terrible, is at least about the civilization, a consequence of its choices, something it could in principle have done otherwise. A gamma ray burst is not about anyone. The star that fires it does not know the target world exists. The beam was set in motion by physics that ran its course thousands or millions of years before it arrives, aimed at nothing, indifferent to whatever happens to be in the way. There is no malice and no meaning in it, which is somehow worse than malice, because malice at least implies you mattered enough to be a target. A civilization ended by a gamma ray burst is ended the way a candle is put out by a draft from a door opening in another room, an event that had nothing to do with the candle, and did not notice the candle, and would have happened identically if the candle had never been lit. To last, a civilization would have to survive not only its own choices, but the absent-minded violence of a universe that is not aiming at it, and would extinguish it without ever knowing it was there. That is the part that makes these cosmic threats different from the self-inflicted ones, and worse in a particular way. There is no choice involved, no mistake, nothing a wiser civilization could have done differently. A gamma ray burst gives no warning, because it arrives at the speed of light, which means the light that would warn you and the radiation that would kill you arrive at the same instant. You cannot see it coming because there is nothing faster than it to carry the news. A civilization could be doing everything right, could have solved every problem of its own making, and simply have the bad luck to sit in the path of a beam fired long ago by a star it never knew, and that would be the end, through no fault and no failure of its own. The Ordovician case is worth sitting with, because it is the closest thing we have to a real example of the universe reaching in and ending a chapter of life, for reasons that had nothing to do with the life itself. About 440 million years ago, in the late Ordovician, Earth suffered one of the largest mass extinctions in its history, a die-off that wiped out a huge fraction of the species then alive, most of them ocean creatures, since that is where complex life mostly was. The cause is genuinely debated, and I will not pretend it is settled, but one serious hypothesis, argued by researchers including Adrian Mellett and Brian Thomas, is that a gamma-ray burst played a role. The pattern of which creatures died fits, in some analyses, what you would expect if the ozone layer had been stripped and ultraviolet light had flooded the upper oceans, killing the plankton at the base of the food chain and starving everything above it. We cannot prove it. The burst, if there was one, left no crater, no ash layer, nothing but a pattern of death consistent with a sky that briefly turned lethal. But that is exactly the point. A threat that arrives as pure radiation leaves almost no trace except the bodies, which means we might have already been touched by one of these once long ago and only barely be able to tell. And the gamma-ray burst is only the sharpest of a whole category. A supernova, an ordinary exploding star, if it went off within about 30 light years of an inhabited planet, could damage that planet's atmosphere badly enough to threaten everything on it, flooding it with radiation and disrupting the chemistry that protects the surface. We know these happen near us. There is a radioactive form of iron, iron-60, that is made in supernovae and almost nowhere else, and we find it in the sediments at the bottom of Earth's oceans, laid down a few million years ago, the fallout of supernovae that exploded close enough for their debris to reach us. The universe has been setting off these bombs in our neighbourhood throughout Earth's history. We have simply been lucky so far that none was close enough or aimed well enough to end us. Add to that the asteroid impacts, the ones that have caused mass extinctions before and will again, and you have a steady drumbeat of external threats that have nothing to do with how wise or foolish a civilization is. I find the iron-60 in the seabed genuinely haunting, so let me dwell on it, because it is the most concrete proof we have that the universe really does reach into our neighbourhood. Iron-60 is a radioactive form of iron, and it is made almost exclusively in supernovae, in the explosions of dying massive stars. It decays away over a few million years, which means any iron-60 that was here when Earth formed would have vanished long ago, and yet we find it, laid down in distinct layers in the sediment at the bottom of the deep oceans and in the crust of the moon. The most studied layer was deposited a few million years ago. The only way it could be there is if it fell onto Earth recently, in geological terms, which means a supernova exploded close enough to us within a few hundred light years a few million years ago and sprayed its debris across the solar system, and some of that debris settled through the oceans and onto the seafloor, where it sits now, a thin radioactive signature of a star that died near us while our ancestors were already walking the Earth. We have in the seabed the physical ash of a nearby stellar explosion. The universe has been setting off these bombs in our vicinity throughout our history, and we can hold the proof in our hands. We have simply been far enough each time to survive it. But picture what that means out there. Somewhere within a few hundred light years of here, more than once, a massive star reached the end of its life and collapsed and detonated, briefly outshining every other star in the galaxy combined, throwing its outer layers into the dark at a fair fraction of the speed of light. And that shell of debris expanded outward for thousands of years until it washed over the solar system, sleeting through this planet, settling into the ocean floor, where it still sits. The light of those deaths would have been bright enough to see in daylight. Our ancestors may have looked up at a new star that had not been there the night before, not knowing they were watching the same explosion whose ash we would one day pull from the seabed. The asteroid is the one of these we understand best, because it has the clearest fingerprint in our own past. 66 million years ago, an object somewhere around 10 kilometers across struck what is now the coast of Mexico, and the dinosaurs, along with most of the species alive at the time, did not survive what followed. That was not the only one. The history of life on Earth is punctuated by these impacts, spaced out across the eons, each one resetting the board. And the thing about an impact is that it does not care in the slightest about the sophistication of whatever it lands on. A civilization that had cured its diseases, ended its wars, balanced its planet perfectly, and lived in peace for 10,000 years would be just as vulnerable to a 10-kilometer rock as the dinosaurs were, unless it had specifically developed the ability to see the rock coming and move it, which is a capability we are only just beginning to reach for ourselves. So the impacts are another flood, another threat with no relation to a civilization's virtue, arriving on the universe's schedule rather than anyone's choosing. The one mercy is that, unlike the gamma ray burst, an asteroid can in principle be seen coming and deflected, which means it is the one cosmic flood a civilization might actually learn to control, but only if it survives long enough and looks outward hard enough to be ready when the rock arrives. The analogy I keep reaching for is a house and the difference between fires and floods. We have spent most of this video on the fires, the dangers a civilization creates inside its own house, the self-destruction, and the planetary bottleneck, and a careful enough household might learn to prevent every fire it could start. But a house that has solved all its fires still sits on the land, and the land floods sometimes, from rains that fall far away and have nothing to do with the house at all. The gamma ray burst, the supernova, the impact, those are the floods. You can be the most careful homeowner in the world, never leave a stove on, never fray a wire, and still wake to water rising through the floor from a storm you had no part in and no warning of. Surviving your own fires does not move you off the floodplain. And the universe, it turns out, is one enormous floodplain. The detail people get wrong about the sun is worth correcting, because the real deadline is much sooner than the famous one. Everyone has heard that in about 5 billion years the sun will swell into a red giant and swallow the inner planets, and that is true, but that is not when Earth becomes uninhabitable. That happens far earlier. The sun is slowly, steadily getting brighter as it ages, brightening by about 10% every billion years, and that slow increase is enough that in roughly 1 billion years the sun will be hot enough to push Earth past the point where it can hold liquid water at its surface. The oceans will heat, evaporate, and be lost to space, and the planet will become a sterilized rock, while the sun is still an ordinary middle-aged star, billions of years before the dramatic red giant ending everyone pictures. So a civilization on its home world does not have 5 billion years. It has more like 1, before its own star quietly turns the planet into something like Venus. To last beyond that, it would have to leave to move to another world or another star, which means crossing exactly the enormous dark we know almost nothing can cross. The slowest threat is also the most certain, and it has a deadline. And then, beneath all of it, the slowest threat of all, the one that comes for everyone who somehow survives all the rest. Stars age, stars change. Our own sun is slowly growing brighter, and in about 1 billion years it will be hot enough that Earth can no longer hold liquid water at its surface. The oceans boiling away, the planet sterilized, long before the sun swells into the red giant that will eventually swallow the inner worlds entirely some 5 billion years out. Every civilization that stays on its home world faces this eventually. The star that gave it life turns on it. To survive past that, a civilization would have to leave, to move, to cross the very dark we have spent so much time on, and we do not know if that is even possible for anything alive. And even leaving only buys time, because the new star ages too, and the one after that, so that truly lasting would mean moving again and again, forever, staying one step ahead of the deaths of stars for as long as there are stars to flee to. So lasting, truly lasting, does not mean surviving one bottleneck. It means surviving an unending series of them, the self-inflicted ones, and then the floods, and then the slow death of your own star, forever, with no point at which you are ever finally safe. That sounds like a sentence of doom. It almost sounds like the answer is obviously that nothing can last. But the same framing that makes it sound impossible, when you turn it around, tells us something genuinely useful about what survival would actually require, and whether it is a thing that can be learned. Go back to Adam Frank's models for a moment, the ones that scared us in the third section, the coupled simulations of civilization and planet, where so many runs ended in die-off and collapse. I gave you the dark half of what they found. Here is the other half, and it matters just as much. Not all the runs ended badly. Some of them, with the right choices at the right time, found the soft landing. The civilization grew, strained its planet, and then, before the feedback became fatal, changed the way it used energy and leveled off into a sustainable, steady state, a long-term balance it could hold. The collapse was common in the models, but the survivable path was always there too. The bottleneck was generic, yes, but so, in the very same models, was the existence of a way through it. It is worth being specific about what separated the surviving runs from the collapsing ones, because the detail is where the hope actually lives. In Frank's models, the civilizations that made it were not the ones that used the least energy or grew the slowest. They were the ones that changed how they got their energy before the planet's feedback became overwhelming. In the runs where a civilization kept drawing on the kind of energy source that fed back hard on the planet, that degraded the world even as it powered the growth, the collapse came no matter what, and worse, the runs where the civilization realized the danger and switched too late still crashed, because the feedback already set in motion played out regardless. The survivors switched in time, moved to ways of running themselves that did not poison the system that held them, while there was still margin to absorb the change. So the skill is not restraint exactly, not simply using less. It is a timed transition, a change in the kind of relationship a civilization has with its energy and its world, made during the window when it can still make a difference. Miss the window, and even the right change cannot save you. That is sobering and clarifying at once, because it says the test is real and the timing is everything. That changes the meaning of survival in a way I find genuinely important, so let me be careful with it. If the bottleneck were pure bad luck, a roll of cosmic dice, then surviving it would just mean being lucky, and there would be nothing to learn and nothing to do but hope. But that is not what the models show. They show that the difference between the runs that collapse and the runs that survive is not luck. It is a specific transition, a describable change in behavior, made at the right time. The survivors are the ones that shift from unconstrained growth, from consuming more and more as fast as possible, to a stable relationship with the energy and the planet that sustain them, before the planet forces the change on them through collapse. Survival, in these models, is not a stroke of luck. It is a skill, a particular, identifiable maneuver that a civilization either performs in time or does not. Adam Frank has a way of putting this that I find genuinely steadying, even though it changes none of the facts. He says we should think of ourselves not as uniquely sinful, but as cosmic teenagers. A teenager is someone who has suddenly come into real power, a body that works, a mind that reaches, the capacity to do serious damage to themselves and others before they have developed the judgment to handle any of it. And the teenage years are dangerous precisely for that reason, the gap between capability and wisdom. But they are not, for most people, fatal. They are a passage, a hard one, that can be come through. Frank's argument is that a technological civilization hitting its planetary bottleneck is a planet going through adolescence, and that the right response is neither the despair of we have ruined everything, nor the denial of nothing is wrong, but the harder, more useful stance of a teenager learning to grow up, which is to say, taking the danger seriously without treating it as a death sentence. I find that helpful, because it holds both truths at once. The danger is real, adolescence kills some people, and the passage is survivable. Most teenagers become adults. Which of those our civilization turns out to be is exactly the open question, and the framing at least tells us it is a question and not a verdict. And if it is a skill rather than a stroke of luck, then our own situation looks completely different than it did an hour ago. Because a skill can be understood. A skill can be named, studied, practiced, taught. If what we are going through, this moment of straining our planet by using energy at a scale it cannot absorb, is not a unique human disgrace but a generic transition that every technological civilization faces, then we are not uniquely doomed and we are not uniquely wicked. We are taking a test that in principle has a passing grade, a test that the physics says is passable, even if we do not know how many actually pass it. That reframing from moral failure to general transition is the single most useful idea in this whole subject, because a unique disgrace is something you can only feel bad about, but a generic test is something you can actually try to pass. A test has a method, a test can be studied, and a test that others may have failed is still, for the one taking it now, a test that is not yet over. There is a real lesson hiding in why a bike is so hard right up until it is easy. A bicycle is unstable when it is slow, and actually becomes more stable the faster it goes, which is the exact opposite of what fear tells you. Every instinct in a wobbling beginner says slow down, put your feet down, be careful, and every one of those instincts makes the wobble worse because stability comes from moving forward with enough commitment to let the balance find itself. The thing that feels safe, slowing and hesitating, is the thing that drops you. I think the bottleneck a civilization faces may have something of this counterintuitive shape. The instinct, when you realize your growth is straining your planet, might be to simply stop, to freeze, to cling to what you have. But the survivable path in the models is not freezing. It is a transition, a change in how you move, made with enough commitment and enough timing to carry you through to a new kind of balance on the other side. Not stopping, but changing how you go. The wobble and the balance are the same motion, and the difference is whether you lose your nerve in the middle of it. I do not want to push the analogy further than it can bear, but the shape of it, that the way through feels like the way down right up until it doesn't, seems true to what the models show. The analogy that fits is learning to ride a bike. There is a stretch, right in the middle of learning, where the wobble feels exactly like falling, where every instinct screams that you are about to go down, and many people do go down again and again. It genuinely is the hard part. But the wobble is not the same as falling. The wobble is what becoming balanced feels like from the inside, right up until the moment it resolves into balance, and you are riding. From inside the bottleneck, the strain and the danger and the feedback all feel like the beginning of the end, like falling. And for many civilizations in the models it is. But the same wobble, navigated correctly, is also exactly what the transition to lasting feels like from the inside, right up until the moment it becomes balance. The danger and the survivable path are not two different roads, they are the same road, felt from inside the hardest part of it. I will not oversell this, because the honest uncertainty is still enormous, and I promised you honesty. We do not know whether any real civilization has ever actually made this transition. The models show a path exists in principle, but they cannot tell us how likely the survivable path is against the collapse paths, whether it is 1 run in 3 or 1 in 1,000. We do not know if the passing grade is common or almost impossible. We are still reasoning from simulations with made-up numbers and from a single example ourselves that has not finished its own test. So I am not telling you survival is likely. I am telling you something more modest and, I think, more useful. Survival is not obviously impossible, and it is not obviously luck. There appears to be a skill to it, a thing that can in principle be done on purpose. And that turns the whole question from a prophecy we await into a problem we face. Which brings us, finally, to us. to where we actually stand right now in this argument. Because there is one more thing about that final term, the L we have been circling for 2 hours, that I did not fully understand until I had walked all the way through everything else. There is something strange about being inside the very thing you are trying to measure, and it is worth naming clearly. When an astronomer measures how fast stars form, they stand outside the process and watch it. They are not themselves a star, but when we try to estimate L, the lifetime of civilizations, we are not standing outside it. We are one of the things being measured, and we are in the middle of our own measurement, and the number we most want to know, our own lifetime, is not a fact sitting in the world waiting to be read, but an outcome still being produced, partly by what we do. It is as if the thermometer could change the temperature, as if the act of measuring were also an act of making. For every other term in the equation we are observers. For this one, for our own value of it, we are participants. And that is not a comfortable place for a scientist to be, because it means we cannot simply discover the answer the way we discover the other terms. We are in part deciding it in real time, without being able to step back and see the result, because the result is not finished and we are the ones still writing it. We have been a civilization that can be heard for about 100 years, and we do not know how long it will last. Think about where that actually places us in the picture we built. We are not a civilization looking back on its long survival, secure in having lasted, and we are not yet a civilization that has ended. We are a civilization in the first instant after the strike, still flaring up, the flame not yet steady, at the single most dangerous and most undecided moment of the whole burn. Everything this video has described, the self-destruction, the bottleneck, the brief flare, the silence, all of it converges on exactly the moment we are standing in right now. We are 100 years into being loud, deep in the part of the curve where, if the dark reading is right, most civilizations are lost. We are not observing the bottleneck from outside, we are in it, in the narrowest part of it, at the exact stage where the matches in the dark room tend to go out. That is not a comfortable thing to realize, but it is the truth of where we are, and there is a strange clarity in naming it plainly. We are at the dangerous part, we are in it now. That is the entire length of our flare so far. We do not know our own L. Now normally, when a scientist faces an unknown number, the job is to go measure it, to find the value that is already out there waiting to be discovered. And that is exactly what we do with every other term in the Drake equation. How fast are stars born? Go measure it. How many have planets? Go measure it. Those numbers are facts about the universe, already true, sitting there for us to read. But L, for us, our own L, is not like that. And this is the thing that took me the whole argument to see. Our own L is not a fact already written somewhere, waiting to be discovered. It is not a measurement we take. It is a thing we are, right now, in the middle of doing. There is a humbling way to see our position that I keep returning to. We are, so far as anyone can tell, the only experiment in this question that we can actually observe from the inside. Every other civilization, if they existed, ran their version of this test and finished it long before we could watch, their result already written, already dark. We cannot learn from them because they left no record we can read. So we are not just taking the test, we are for ourselves the entire data set on whether the test can be passed, a single experiment still running, with no control group, no prior results to study, no one to ask. That is a lonely place to stand scientifically, but it also means something strange and almost vertiginous. Whatever we do becomes, for any later civilization that might wonder about us the way we wonder about the ones before, the only trace we leave of whether a young, loud civilization can grow old. We are writing the one data point we have, and possibly a data point someone else will someday try to read, and we are writing it now, without knowing how it ends, which is the only way it has ever been written by anyone. I keep having to remind myself, and you, how little we actually have to reason from, because it is the most honest thing in this whole subject. One example. That is our entire data set on the lifetime of technological civilizations. One, and it is us, and we are a century into it. And the century is not over. Everything I have told you tonight, the self-destruction worry, the generic bottleneck, the brevity of the flare, the reading of the silence, all of it is built on top of that single unfinished example and a set of models with numbers we made up because we had no real ones to use. I believe the argument. I think the silence genuinely points toward a small L, and I think the bottleneck genuinely looks generic, but I would be lying if I dressed it up as more certain than it is. We are one example, recently begun, trying to work out from our own brief existence how long such things tend to last, with no other case in sight to compare ourselves to. That is not a position of knowledge. It is a position of honest, careful guessing, and the most truthful thing I can say about our own L is that we do not know it, cannot know it yet, and are in the process of finding it out by living it. That is what makes the last term different from all the others, uniquely different. Every other factor in that equation is set by nature, and we are just spectators reading the result. But the lifetime of our own civilization is not set yet. We are inside it. We are writing the value with everything we do or fail to do in this century and the ones that follow, if there are ones that follow. The silence out there may well mean that the typical L is small, that the typical civilization burns fast. The history and the models and the bottleneck all lean that way, and I am not going to pretend they do not. But the typical value is a fact about other civilizations already finished, already dark. Our value is not finished. Ours is the one number in the entire equation that is not a measurement but a choice still being made. The only term whose value for us is at least partly in our own hands. And I want to be careful not to turn that into a cheap inspirational line, because it is heavier than that. Partly in our own hands does not mean fully in our control, and it does not mean survival is likely. The cosmic floods are still out there, indifferent to anything we decide. But the part that is ours, the part about whether we navigate our own bottleneck, whether we make the timed transition the models say is possible, that part is genuinely undetermined, genuinely open, genuinely still being written by what a civilization does in the window it has. Most of the equation is a report on a universe that already is. This one term for us is a question still being answered, and we are the ones answering it, whether we attend to it or not. And that is the strange place this whole dark argument finally arrives at, and where I want to leave you with what I actually think it means. Here is what I keep coming back to. We started with an equation, and a single term in it that nobody can measure, and I have spent this whole time telling you why that term, how long a civilization lasts, might be small, might be the thing that almost nothing survives. And I believe that is a real possibility. The silence is real. The bottleneck looks generic. The universe does seem to keep making light and watching it go out. But there is one thing about that term that is different from every other number in the equation, and I did not see it until late. Every other factor is a fact about the universe that we go out and measure. How many stars, how many planets, how often life begins, they are already true, and we are just reading them. The last term for us is not like that. We are still inside it. Our own number is not finished. It is not a fact we discover. It is a thing we are doing right now in the only century we have so far been able to be heard. So I think the terror and the hope are the same fact, seen from two sides. No civilization may ever survive, or everyone that does is a civilization that decided to. We are a match that has just been struck. We do not know how long the flame lasts, and nobody is going to tell us. But the one thing a flame gets to do while it is lit is give light, and ours is lit now. If you want more of these, the hard questions followed all the way to the honest end. Subscribing is how you keep them coming. Sleep well